start the final topic of this section, which is the comparison test. And to understand the comparison test, it is easy if we visualize the integral as the area under a certain curve, right? Okay, so I will explain it with this example. Okay, so here I have drawn two graphs in the same plot. The two functions, I represent it as fx and gx. Gx is in red color, fx is in this purple like color. Okay, so here you can see in between the region A and B, fx is larger than gx. Okay, and in between this region you can see g is greater than f, and here you can see once again f is greater than g, and here g is greater than f, and here from here onwards we can see f is greater than g. Okay, so what will happen to the area? So if we consider the area from A to B, that means within this region, is which one is larger? If we consider the area within the same region of two functions, what is larger? Now here we saw that the function fx is greater in between A and B. So that means f will cover a larger area than g. So we have this relationship. And here within this region g is greater, right? So in this case f was greater than g. And similarly we can see at each of these regions, depending on the comparison between g and f, the values of the integrals can also be compared, right? Say for example, in between b and c, g is greater than f, so the integral of g is greater than integral of f. And in between c and d, f is greater than g, so the integral of f is greater than integral of g. And here g is greater than f, so the integrals will follow the same order. And also now see, according to the picture that I have drawn, we can say after e, f is greater than g. So after e we have f is greater than g. That means we can even, like the comparison theorem says, we can even compare the improper integrals with the same nature of the comparison of two functions, right? We can even do that for an improper integral. And there is another thing that I need to highlight here. See, none of these functions go below the x-axis, right? None of these functions will go below the x-axis like this, right? So for the comparison test to work, all these both these functions that we are going to compare should be greater than or equal to 0. It cannot be a negative value, because if it is a negative value, then the area or the integral value for this negative terms will be a negative value, and then things will be a bit complicated. So to use this comparison test, or to use this fact that I mentioned, both functions must be non-negative. It can be 0, so you can compare even if it is 0 as long as you have these relationships, but we have to make sure that none of these functions are negative. And also this is true even when you have this greater than or equal to sign. Okay, so it need not to be the strict inequality all the time. So only difference is that if you have the greater than or equal to sign, then that property will be inherited to the integrals as well, right? So when you have the greater than or equal to sign, you will get it everywhere in the integral also, right? So if I summarize, like if I mention it as a theorem with precise statements, it will go like, well, before writing the general statement, I will explain it a bit more. Now, we saw that the improper integrals can also be compared, right? Now, we also learned a definition called convergence. So what do we mean by convergence for an improper integral? Let's take type 1. So what we mean by convergent, what we mean by a convergent integral is that you will get a finite answer for the given integral. Say for example, if this is convergent, that means this will have a finite answer, right? In other words, we can say that starting from E, this function will have a finite area in between, I mean below this function f, right? Starting from E. And so if this larger function converges, that means if it has a finite area, what can we say about the smaller function? So as we saw that these areas can be compared, and if the larger function has a finite area, then it will definitely imply that the smaller function will also have a finite area. Okay, because this smaller function, the area of this smaller function is enclosed within the area of this larger function. Okay, that's basically the key idea of this comparison test. The area of the smaller function is enclosed within the area of the larger function. So if the larger function has finite area, then definitely the smaller function will have a finite area, right? And on the other hand, if the smaller function has a infinite area, so if this explodes, then definitely the larger function will have an infinite area because of the same reason. Now that means even the smaller guy is very big, so definitely the larger one is going to be a definite divergent integral, right? So but it will not work in the opposite direction. It's like if the larger function diverges, that means if the larger function has an infinite area, we cannot say anything about the smaller function. Okay, so if this larger function has an infinite area, there can be a smaller function with a finite area, and also there can be a smaller function with an infinite area as well. And also if the smaller function has a finite area, we cannot say anything about the larger function. The larger can the larger function can sometimes have a finite area, and it may also have an infinite area. Okay, so this comparison theorem will work only in one direction. Okay, so you don't have to like by heart each and every word of this theorem. Only thing is that try to visualize this as a area problem. Okay, so if the small, like if we have two things like this, if one is enclosed within the other, and if the smaller guy explodes, then the larger one should definitely explode. In other words, if the smaller one diverges, then the larger one will definitely diverge. And if the larger person is finite, then there is no space for the smaller guy to explode. So definitely the smaller person will also converge. Okay, so if we write down the things that we discussed as a statement or as a theorem, then we can have it like this. So if you have two functions which are continuous, and this is also important, okay, it should be continuous with now this is the way we are going to compare. F is greater than or equal to gx, and gx is greater than or equal to 0. That means fx is also greater than or equal to 0. In other words, we have made sure that both functions are lie above the negative region. Okay, it can be 0 but not negative, right? So if we have this relationship, then if the larger integral converges, then the smaller integral will also converge, and if the smaller integral diverges, then the larger one will also explode. Okay, so this is basically the comparison theorem, and we will end this section in the next video by doing 2 examples related to the comparison theorem.